This is a set of instructions for predicting molecular geometries. I like all of them except the fourth one. So first thing, draw the Lewis structure. Then determine the total number of electron groups around that central atom. Then look at the number of bonding groups and the number of lone pairs. And then the book says refer to table 11.1. Well, it's not going to help you on an exam because I'm not giving you table 11.1. So that's what I consider bad advice. Cross that out. That's not good. Instead, think about how balloons would arrange themselves. That'll give you the electron geometry from the number of groups. And then imagine that any lone pairs are invisible balloons and name that shape. Okay? So this question could be an exam question. Predict the molecular geometry and bond angle of Cl and O. It's not specifically telling us what the central atom is, but it's reasonable to assume that it would be the one that's in the middle of the formula. And actually, we'll get the same geometry regardless of how we stick this together. So let's put the nitrogen in the middle and the chlorine and the oxygens around it. Excuse me. You have to have bonds in there. We have to count up the valence electrons. So chlorine has 7. Nitrogen has 5. That's 12. Plus 6 for oxygen is 18 valence electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. I don't have enough electrons to give everyone an octet. So now what do? We share. It's like Robin Hood. You take from the rich and you give to the poor. Oxygen doesn't have enough. Nitrogen does. So we're going to ask nitrogen to share one of its lone pairs with oxygen. We have not changed the number of valence electrons. We've just put them around in different places. So is this a good Lewis structure? Yeah, we've got octets on everything. If you look at the formal charges, we've got 0 formal charges as well, so that's nice. Okay, so there's our Lewis structure. How many electron groups on the central atom? 3. A double bond, a single bond, and a lone pair. So how do 3 balloons arrange themselves? They're going to make a triangle, right? A flat triangle. So the electron geometry would be trigonal planar. So that's the electron geometry. Sometimes we abbreviate that EG. It's not asking for this, but we're going to write it down anyway. So that's trigonal planar. And then to find the molecular geometry, we look at any lone pairs and make them invisible. So take this guy, and that's a lone pair. And one of these is a double bond, which is not a big deal, but we could show that for sure. So the molecular geometry is what? Bent. And then it wants the bond angle. Well, this is the bond angle. It's the angle between the bonds. We're not looking at the angle between a lone pair and bonds. We're looking at the angle with the bonds. So if this was a perfect trigonal planar structure, what would the angle be? 120. So is this going to be less than 120 or greater than 120? Less, because this guy over here is very repulsive. And so these guys hate each other less than they hate the lone pair. So the angle will be less than 120. Exactly what the angle is not something that you can easily predict. So we'll just say it's less than 120. Any questions? I3 minus. Does that one sound familiar? I think that was on the worksheet, wasn't it? Okay, so we got 3 iodines. We'll connect them together. 3 iodines, they each have 7 valence electrons, and then the negative charge tells me there's an extra electron. So I add 1, I've got 22 valence electrons. And so I'm going to start throwing these around. I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I've got octets for everybody, right? But I have another pair of electrons. Where do I put them? We'll put them on the central atom. So I'm going to move these guys over a little bit. Iodine is in period 5. It can expand its octet. And if we're going to expand an octet, we're going to do it on the central atom as opposed to expanding one of these guys. Just because I told you. And then, just to be really complete, we should put brackets in a charge. Lewis structure. And typically what I would do on an exam is I would give you the Lewis structure and ask you for the geometry. And typically I'll ask you to draw the Lewis structure as a separate problem. So how do we determine electron geometry? How many groups on the central atom? How many groups are there? 5. 5 balloons makes what shape? Oh, I accidentally paused it in there, so I don't know what we missed. Let's just go back here and show that in case this didn't show on the video. That's what we ended up with, linear bond angle of 180. There's a hair. Okay, so a lot of these shapes are 3-dimensional, and we need to be able to represent those on a piece of paper, a 2-dimensional surface, or a screen, right? So how do we do that? Well, we use just a regular line to indicate something that's lying in the plane of the screen or the paper. This hatched wedge, kind of like a dashed line, that's behind the screen. It's not solid because you can't really see it. It's behind the screen. And this one is solid, and this one's jumping out at you, okay? So when we look at this tetrahedron here, this is how we would, just write it, and this is the representation of it. So here we have the A, and these 2 X's are in the plane of the paper. This X is sticking out in the front. It's sticking out like this. And that one is back here. You can't see it. Okay? What if we have more than one interior atom? And we don't call them a central atom anymore. We call it an interior atom. Well, then what we're going to do is we're going to look at the geometry around each of the interior atoms. So here we have the Lewis structure for glycine, an amino acid. And there are 4 interior atoms, atoms that are bonded to more than just one other atom. So we can look at each of them. So we look at this nitrogen, and we see there are 4 electron groups, which would make a tetrahedron, but there's a lone pair, so that would become a trigonal pyramid. This carbon has 4 electron groups, no lone pairs, so that's going to be tetrahedral. This carbon has 3 electron groups, which is a trigonal planar, and no lone pairs, so it remains trigonal planar. The oxygen has 4 electron groups. The electron geometry would be tetrahedral, but 2 of those balloons are invisible, and so we call that bent. So I probably will give you a Lewis structure like this on an exam and ask you for the geometry around one or more of those interior atoms. I will not ask you to draw things because I don't want to be in the position of having to judge whether your drawings are correct or not. That doesn't sound fun. But you might have to draw things on a worksheet. In fact, you definitely do. Or on Mastering Chemistry, they might make you do something with that stupid program. So here, predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. So they've kind of given us a structure here, but this is not a full-on Lewis structure, right? We need to know where all the lone pairs are. So we need to flush this out a little bit. And there's going to be lone pairs on the oxygens. H3C, so this is telling us that these 3 hydrogens are all on the carbon. Okay, so now I can look at this carbon and say, how many electron groups? 4, and no lone pairs. So what's the geometry for that one? Tetrahedron. And this guy, how many electron groups? 3. Any lone pairs? No. 3 balloons make what? A flat triangle, right? Trigonal planar. And then over here, 4 electron groups. Electron geometry is a tetrahedron, but 2 lone pairs. So what do we call this? Bent. The strategy when trying to sketch this molecule is you want to have as many of those atoms as possible be in the plane of the screen. It's just a lot easier that way. So I'm going to start with the tetrahedral one because that one is the hardest. And so here's a carbon, and it's going to have 2 in the plane and 1 sticking out and 1 sticking back, right? So those are atoms. So that's that first carbon, and this is the second carbon. And this is going to have a double bond to an oxygen and a single bond to an oxygen. Oh, it's not a very good angle. So there's the double bond, and there's the single bond to the oxygen. And so this angle is going to be roughly 120. So here's my other oxygen, and this one has 2 lone pairs. I'm going to make those be out of the screen, in front and in back, and there's my hydrogen. So that's a sketch of the molecule. What's the molecular geometry about nitrogen in CH3NH2? So these are organic compounds, lots of carbons and hydrogens, and so typically how we show these formulas to hint at the structure, CH3, these H's are after the C because they're on the C, and these H's are separate because they're on the nitrogen. So we've got a carbon with 3 hydrogens bonded to a nitrogen with 2 hydrogens. And we're looking for the electron geometry around this nitrogen. We need to get all the lone pairs in there. So fast forward, there we go. So what's the molecular geometry about nitrogen? Don't all talk at once.
Trigonal pyramidal?
Yeah, it's a trigonal pyramid. Now you could say letter C.
But the words are
The words are fun. Some people don't like to try to say the words though. So either one's fine. So I'm looking at this, I've got 4 groups, right? 4 balloons make a tetrahedron, make one of them invisible, and I have a triangular pyramid, a trigonal pyramid. Any questions?